My dear friends and dear Professor Karakaya, welcome to our hyperparameter tuning and model selection presentation. I am Tan from Computer Engineering Department, and our team members are Aysu from Software Engineering Department, Roşna from Computer Engineering Department, Rıza from Electric and Electronics Engineering Department, and Galiphan from Mechanical Engineering Department. Next, please. We will begin our presentation with the introduction section where we give information about our dataset. After that, me and Roşna will talk about pre-processing. Continuously, Galiphan, Aysu, and Rıza will describe the hyperparameter tuning section with 3 different models. Finally, we will end our presentation with conclusion. Next, please. Our main objective is to analyze the overall prices of flight tickets and provide insights about the pricing of the flight tickets. And our aim is determining the influences on the flight ticket prices and determining the variation in prices according to some features. Next, please. Our dataset is taken from Kaggle.com. It has 300,261 distinct flight booking options. As you can see in the right part of the screen, there are 11 features collected from easymytrip.com. This is an supervised dataset, and because we are trying to predict the price of a flight, we will use a regression model. Next, please. When we looked at the raw data, we first removed the features called feature 1 and flight. These extracted features are uniquely defined for each sample and have no effect on the model. Next, please. When we view our raw data using data table widget, we see that only 2 of our 9 features are numeric and the remaining 7 are categorical, and price is our target. Next, please. Before we move on to pre-processing part, as you know, we will present it again, as we did not do this part correctly, which we should have done in previous presentation. For his feedback, we would like to thank Professor Dr. Murat, Karakaya. We hope we got it right this time. Next, please. I will start pre-processing by introducing our base model. Due to its compatibility with our model, we performed our pre-process steps using decision tree. Decision tree algorithm belongs to the family of supervised learning algorithms. Unlike others, the decision tree algorithm can be used for solving regression and classification problems. The goal of using decision tree is to create a training model that can use to predict the class or value of the target variable by learning simple decision rules. In other words, if-else conditions inferred from prior data training, like training data. As you can see on the right of the screen, we did not interfere with the decision tree widget by leaving the settings as default. Next, please. First, we encoded the categorical features and converted them into numerical values, and the final version looked like this. Encoding is a technique of converting categorical variables into numerical values so that it could be easily fitted to a machine learning model. Each number represents a word belonging to the feature. Then we just gave our encoded data to the model as it was and examined the results. Next, please. When we look at the results as train and data test, although our R2 values are good, we have very large error levels. Although this is not unexpected, we scaled and reduced the errors in the future. Next, please. Then we scaled our encoded data and pulled it between 0 and 1. Scaling technique brings the data points that are far from each other closer in order to increase the algorithm efficiency and speed up the machine learning processing. You can see the final version of the encoding and scaling data below. Next, please.
Tan, may I interrupt?
Yes.
In the previous slide, it is not often seen that we don't see like that, and we don't do this. Check out the names of the features. So the departure time cannot be normalized in that way because we know that it's hours of a day. Source
No,
string
it's
encoding, right?
not. No, it's not our in departure time. We actually have a categorical value like evening or night or morning.
I see,
It's
I
like
understand. So it's categorical values. We don't
yeah.
scale the categorical values. That's what I'm trying to say. For example, source
Okay,
scale, they are just categorical values. We are just scaling the continuous values. So the airline,
okay,
the source, the departure time, arrival time, destination city, class cannot be normalized, okay, or scaled.
okay, okay,
But the category, the continuous values like maybe duration or the price itself, but it's the target value. So in another way, we don't mostly scale the target value, but you can do it.
okay.
But mostly we scale the features, the continuous features, not the categorical features. Okay, please
Yeah,
correct this. Okay, it's not a good idea to apply scaling or other methods like this for the categorical features. We only apply this mostly for the continuous features. Okay.
okay, okay. Sorry, teacher. Uh, Next, please. When we compared encoded only results with both encoded and scaled results, we see a big drop in errors. In most machine learning projects, these are done in a fixed basis. However, we wanted to make this comparison to show their importance. The pre-processing of operations to be performed after this slide will be based on the results of the encoded and scaled data results. Next, please.
Tom, can I ask a question here for you?
Yes.
So if you notice that when you say that scaled data
Yeah.
compared to the left side on encoded, you notice that R square scores does not change, right?
Yes.
That's what we expect because the scaling does not change the R2 scores in that sense. Okay. However, if
Yes.
you check
Exactly.
that mean square error, it goes to like 0.00, so in train,
Yes.
and test 0.001. Can you explain me why it's like that?
Because like in the first part, let's say the ticket price is like $300,
Yes.
and our maybe prediction is like $350. When we scale them into 0 and 1,
Yes.
it's, I mean,
Okay, you know what you
can
do.
be
So
max.
therefore,
Yes.
mostly we don't do scale the target value.
Yes.
Okay. Otherwise, it is
Actually,
unreasonable to use MSC kind of methods because if you scale the target value, then you unscale with the scalar, whatever the scalar
mhm,
is. If you divide by 4, for example, you have to multiply by 4 again to convert your prediction to the scale version. Then you need to
yes.
compare the errors and, of course,
Yes.
the other metrics depending on that error. Do you
Yes.
understand my
This
point?
was Yeah, I know. This was the decision we made like 2 hours ago. We noticed that problem too because after scaling, mean absolute error max it can be one. It's only one because we scaled down into 0 and 1. But we didn't want to show
For
the
your final presentation and final report, I am repeating again. Do not scale categorical features. Scale
yes,
only if it is reasonable continuous features. Mostly do not scale the target values. If you scale the target values for your predictions, you need to first unscale or reverse
yes,
scale, okay,
yes,
the prediction and then compare the other values, the ground truth with the prediction in the unscaled version to be
yes.
fair about your prediction performance. I think it's clear, right?
Yes, we worried that our mean absolute error and other error values are too high, but as an approach, we could have done these price points are in Indian rupees. So it's on, we have to multiply them on 0.012, I think, to convert them into dollars. When we convert them into dollars, it makes much more sense than this. But we stayed on Indian rupees, so errors were really high. So we decided to go with the scaling, but we know I
Yes.
mean,
You
our
understand me,
error.
so do not scale if it is in dollars, make it dollars, for example.
Okay. Yeah.
Because in the end, you are gonna predict some price, right? For a flight.
Yes.
So
Yes.
what you are gonna say? You are gonna say 0.005 what?
Yes.
Right? You need
Doesn't
to
make any
say
sense.
in dollars or whatever the currency in the data set, right? You have to reverse scaling, right? Do you
Yes.
understand my point? So please use the techniques wisely, not blindly. Okay?
Okay.
Please
This
continue.
was our problem, and throughout the presentation, it's going to be a problem, our scaling, but our methods are good. I mean, we worked really hard, and you will like it, I know. But we will change the scaling type, maybe
Okay, in
changing to
your
euros or
final
dollars.
presentation and final report, I don't want to see this. Okay?
Okay. Okay.
Please continue.
Um, as we have seen here, we have compared the test and data results by dividing into. Oh, I'm sorry. Uh, First, I'd like to start by trying an approach left over from our explanatory data analysis presentation. Although it is not exactly a preprocess method, we have seen that we achieved a more uniform distribution by only taking economy class. We analyzed whether we would give better results by giving it to the model in this way. For example, creating two different models. Will that make sense? This is what we are going to decide. Next, please. As we have seen here, we have compared the test and data results by dividing them into three as a whole data set, only economy and only business. Although there is not much difference between them, we observed that when we split the data set, we got lower R2 values and the error values increased slightly. We observed that we lost a feature by dividing the data set and that the number of samples decreased. For this reason, we decided not to divide our data set and continue with a single model. Next,
Just a
please.
moment. First of all, not R2 score, R squares score. Okay, R
R
square,
squares. I'm
not
sorry.
R2, R square score. Secondly, can you tell me why it is inverse what you expected? Why the results do not support your expectation?
I mean, because with dividing the data set, we lose one feature. That feature is class. It's economy or business. We lose one feature, and also, I believe in our whole data set, it has 300K values. But if we narrow it down only business class, we have only 60K samples, and in economy, 240K samples. So because we decreased the one feature and decreased the sample size, that's why we thought our square values are a little bit worse.
Okay, please continue.
Next, we tried to see if we could get better results with feature constructor widget. Since we have only two numeric features, we added new features by doing our operations with duration and days left. First, we analyzed the changes in the result after taking the individual logarithms, and then we multiplied the two features and analyzed them. Next, please. Although we tried both adding it as a new feature and deleting the original, we could not find a difference in the results by taking logarithms. The reason why I wrote no change is that our orange tree values do not change because only 4 digits appear after comma. Next, please. As a result of multiplying duration and days left, there is a 0.001 decrease in the R2 value when added as a new feature. When we look at it by subtracting duration and days left, we observe that our error increased both in train and the test data, and our square value is decreased. As a result, better results could not be achieved with data splitting and new feature generation with feature constructor. Now, Roshna will continue with the second part of the pre-processing.
May I ask a last question?
Yes.
Why don't you think of that adding a weekend feature. If you go back your slides, so there are
Yes.
the days, right? Flight days, I believe.
No, actually, we don't have any flight dates. Days left is the number of days left to the flight. So
There is no
we don't
flight,
know.
there is no day.
No, we don't have any day. These dates only has, I mean, 30 days of flights in India. So we don't have any actual dates on weekend or normal weekday.
Maybe there could be other feature that there is the stops and the duration. Maybe you can
Yes.
multiply them to show that the impact would be higher if you choose some flight. If there are more stops and with longer one, right? So maybe you try this. Okay, thank you. Please continue.
We choose the decision tree as the base model. While we haven't done anything other than scaling yet, our data set train and test rates look like this. When we will show whether the values will get better by processing the values by feature selection. Next, please. First of all, we can see the most important and unimportant factors that affect the target value, which is the price in correlation map. The four most important features are class, airline, stops, duration, respectively. Next, please. We then used one of the feature selection methods, which is lasso regression, to find features are less important than others. The lasso regression algorithm changes the less significant values to 0 as the alpha number changes. These are departure time, destination city, source city, duration, and arrival time, respectively. We removed the most insignificant feature, which is the departure time, and the results were like this. When comparing the data with no feature extracted yet, in the train section, the error values increased and R-square did not change. In the test section, we can see that the error values increase and R-square decreases. We abandoned this method because the values decline when we remove even the most insignificant feature. Next, please.
Roşna, may I ask a question?
Yeah, of course.
Can you explain why the lasso feature selection, using lasso regression method as a feature selection method do not work? Can you have an idea? Because you expressed that it does not work, right? Why not?
Because even our less important feature is has some effects for the value.
Okay,
That's
it's
why.
correct. But also there is one important thing in your data set. Why would you use lasso regression for a feature selection method? Why would you use? When would you use?
Well, I'm not sure.
Anybody in the team? When
I
would
mean,
you?
in the last presentation, teacher, you said
Let's not choose another guy. Okay, you have talked a lot.
yeah.
Thank you. Rıza, have an idea? Aysu, Galiphan.
No, sir, I don't have.
Okay, so actually, if there were many features, right, then you would like to reduce the number of the features, right? But since you have only 10, 12 features, if you lose some of them, it wouldn't help any model almost. Am I right, Roşna?
Yeah.
Yes, please continue.
Can I say something? I mean, in the previous presentation, you said that did you use lasso, and that's why we use lasso.
No,
I
I
mean,
didn't ask. Why did you use? I didn't ask this. I asked that
did
it
you lose?
didn't
Did
help
you
you.
use lasso?
What's your comment about that? The comment is
Yeah.
that we don't expect that it could help you because your feature number already is few.
Yes.
Okay, I am asking your
I
comment. I am not asking why
understand.
you did this. I am asking what would you use this in what circumstances? When there are many features, you can use to reduce the number of features. Okay, please
I
continue.
understand.
Okay, next slide, please. When we tried another feature selection model, which is the K-best method, the K-best feature selection approach ranks all the features based on their importance or usefulness for the task at hand, and selects the top K features. In this method, we selected the 5 most important features and only trained and tested them. The result was worse than the initial version of the data. Values noticeably declined. Therefore, in general, feature extraction did not contribute to the train and test rates of the dataset. We could not get any efficiency from the pre-processing method that Tan showed in the previous slides too. That's why we decided to continue with the data itself without adding or removing any features. Now our other group members will talk about the hyperparameter tuning and model selection.
But I have a reservation for that because you only apply the unnecessary scaling for the categorical values. Don't forget this. In your final presentation and final report, please review all these work, okay?
Okay.
Sir.
It would be maybe changed, right?
Okay, sir.
Okay, please continue.
Okay, so from now on, we will start to make the part of the presentation of the model selecting and hyperparameter tuning. I would like to start with the SVM model,
We
which
have
is
only 10 minutes.
okay. I will be try to be fast as possible then. So I would like to first explain the SVM. SVM is a supervised machine learning algorithm. It hires the dimension of the model and starts to create a hyperline to I guess so stress. I'm so sorry. To create a boundary between the different classes, and since it's mostly preferred on nonlinear separable details and continuous variables, we choose this. But there is a problem during the hyper tuning part. As you can see on the page, we changed the cost different numbers values, and the R2 value starts to become randomly non-positive values. So as we make our research from the internet and the in your comments of the previous year's presentations, this shows the model and our product in the orange is not working on this data correctly. As we change the orange, it doesn't still change. It starts to give random negative values as we change the value of the C. So we don't finish our hypertuning in this model. So for our second model, we choose lasso regression since it's a good model to work with continuous variables, as my friend Roşna gives you information about. So my friend Roşna already gives the explanation of the lasso regression, so I will just pass this page. So we start with the trying to have results without tuning the alpha value. So as you can see on the test and score tables, the R2 value, R square value is have the 0 value. So as we informed from the internet and your lectures, we need to change the alpha value to start to have non-negative or non-zero R square values. So in the next page, as you can see from this page, we try to increase the value of the alpha to get positive values on the R square value, but it's unsuccessful. So we start to go to a lower values of the alpha value, lower than 1. So in the 0.08, we start to get even it's a low result, we get a R square result as 0.19. So in the next page, we start to get even lower values on alpha, and as the R square value increases, the mean absolute error is also starts to become more a stable value. And in these numbers, as you can see, are the significant changes that happen when we change the alpha value. So in the point of 0.008, the R square value is almost become stable. Also mean absolute error, mean squared error, and mean squared error. So we choose our hyperparameter as this 0.008. So in this page, you can also see the test and the train results of these lower numbers. As you can see, there are almost same for most of the cases. I'm continuing. So in the final part, we put the 0.008 to alpha value, and you can see the results of the R square values on test and train data. So from now on, I would like to, if you don't have any questions, continue with my friend Aysu.
Can you go back 2 slides? Okay, here you have several results, but as I expressed in the last presentation, okay, you can show these results like the screenshots from the orange, thank you, but it's a good idea to put them on a figure, right? So the bar chart, pie chart, something, right? Or line chart, so that we can see each of them. Now we are looking left, right, left, right. It's not easy. So you can use the
Yes.
color code, and in a figure you can show. In your final presentation and final report, please put these numbers into a Excel chart, okay?
Yes. Since there are so many different numbers, we train alpha value, we are not able to finish
Okay, please note this.
put on them Excel. So
Okay,
in the final
note
report and
this.
presentation, it will be completed.
Okay, the second point is that I am repeating myself. You are just scale the categorical values in some features. Don't do this. Then try all these tests, experiments again with the unscaled ones. Okay, the data.
Of
Yeah.
course, sir. We will do
All
that.
right, please continue.
Okay, thank you,
We have
Rıza.
only
Now,
7 minutes. We have only 7 minutes.
okay. Now I'm going to talk about AdaBoost, which is a popular machine learning algorithm used for classification and regression tasks. Next, please. First of all, let me explain what boosting is. Then I will explain the AdaBoost and why we choose it. Boosting is a technique that combines multiple weak classifiers into a strong classifier. Each weak classifier is trained on a subset of the data, and the final prediction is made by taking a weighted average of all the weak classifiers' predictions. Next, please. Now let's move on to the AdaBoost. AdaBoost is adaptive boosting, a machine learning algorithm. Its purpose is to create a strong learner by using many weak learners. AdaBoost regression brings together multiple weak predictions and make a prediction using the weighted average of the target variable predicted by each of these estimators. Each weak estimator can be a regression model for a target variable. Next, please. The AdaBoost algorithm trains each weak learner
So if you like, we can pass over these.
Yes, okay, yeah. Okay. In AdaBoost, the number of estimators refers to the number of decision trees or weak classifier used in the boosting process. Each estimator or weak classifier is built sequentially, and each subsequent estimator tries to improve the accuracy of the previous ones by focusing on the samples that were misclassified. Learning rate, a hyperparameter in machine learning, determines the contribution of each individual model in the ensemble models used in boosting algorithm like AdaBoost. Next, please. Now, why we choose AdaBoost? AdaBoost was chosen as the algorithm for this task due to its ability to handle continuous target variables effectively and its capability to combine multiple weak regression models to create a strong prediction model. In addition, AdaBoost is known for its ability to handle complex dataset and its resistance to overfitting. The flight booking dataset obtained from Easy My Trip website is a complex dataset with multiple categorical and continuous features, and AdaBoost was well suited to handle the complexity on the dataset. Next, please. Here you can see how we implemented AdaBoost in the orange tree. Next, please. Now you can see the train and test results we got after tuning the number of estimators. Here at the point where the values started to repeat, the error is low, and where the R-square value is high is 70. We decided to go with this number. Next, please. After choosing our number of estimators 70, we tuned on the learning rate. Here too, we got the best result at 0.6. Next, please. As a result of these tunings, we got the results you see when we apply these parameters, the hyperparameter tuning results, in our test data, unseen test data, and we got the result on the screen. Thank you for listening. Now, Galip will continue.
Hello, I'm continuing with the random forest model. Next, please. Next, please. Random forest is an ensemble method that uses multiple dishes and trees to make predictions. We can continue.
So you can pass this. We know what's the
Okay.
random forest.
Next,
Just
please.
focus on to how you
on this page, on this page you can see the untuned model result with validation test data. When we look at the evaluation matrices, you might say that there can be overfitting, and it looks like model memorized the data. We might say that because their values are low and R-square value is high when we compare the result with validation test scores. Next, please.
Actually, Galiphan, it's not like that. If you consider your mistaken scaled target value, MSC, therefore it is so low. If it
Of course, teacher.
dollars or whatever the currency is, it's not gonna be 0.000.
Of course.
Your mistake, your team mistake. Am I right? Please
Yes,
do
right.
all these experiments with unscaling the target value and categorical values. Don't forget.
Of course, we will do that. To reduce memorizing and possible overfitting, we started with the arranging number of trees, as you can see on the slide. Number of trees equals to 20 and 5. Since there is okay, we can pass this slide. We select the number of trees as 10 to do not make the model more complex. Then I continue tuning with the arranging required number for subset splitting. When I activate the button, I clearly saw that the model's R-square value decreases, so I started increasing number. After 35, errors in the validation test were increased, so I select the number as 35. Next, please. Then I arranged the depth of individual tree. When I activate the button, the R-square rapidly decreased. I saw that the model got better as I
But you
increased
have
the
the experiment results for with the different numbers for the depth and the split subsets more than this. Do you have the results?
I try the combinations like
apply the
60
grid search,
times.
okay, and then provide me a Excel graphic sheet so we can see that what happened, or how the number changes. Okay, we have 1 minute to conclude, please.
Of course, teacher. Next, please. Next, please. Here you can see the tuned model with the unseen test data, we decrease the memorizing on the train, and so as a result, our random forest model gives us a R-square value as 0.985. Next, please. Here is the orange tree flow model for a random forest model tuning. Next, please. To summarize, random forest came to the fore among the models we selected and tuned. We decided to carry out our studies on this model. We will
But we
continue
have to put
tune.
the resulting slide showing with that all the possible values, what we have collected from different models with different parameter values. Where is that summary?
Okay, teacher.
Do you understand me?
Yes, we
Since
understand you, teacher.
their results are too close,
But
we
whatever,
think
you need to
to
put some columns and
Yes, we understand. Okay.
in the final presentation
Okay,
that will
please
be
do.
also
Okay.
added.
Okay,
Uh,
thank you. Thank you for the presentation.
Thank you for listening and your patience.
Okay, thank you. Bye.